We are very happy to welcome Klaudiusz Czudek from Institute of Science and Technology, Austria. And the title of the talk is Random Walks in Quasiperiodic Environment. Please.
Thank you very much. Thank you very much for the invitation. I'm very excited to share my results with you and be here. And before I start, let me mention that the result that I'm going to describe is a joint work with Dolgopyat, and this work was supported by European Union within the Marie Skłodowska Fellowship. So,
Dolgopyat is in the United States or in
Austria? In Maryland, yes, in US, yes, in Maryland. Okay, so this talk in general is going to be about some random walks in the circle. When we apply two rotations, or rather one rotation, forward in time or backward in time, randomly with place-dependent probabilities, later I will define it precisely, but it was very interesting here that there is an important context why we can study this kind of random walks, and this motivation for me is very interesting, and I will devote considerable amount of time to explain that.
So it's not Q plus P is 1.
Yes, that's right. So this context is random walk in random environments, and let me start rather gently with describing the simple random walk on integers. So we pick two numbers, P and Q, positive, as we said, this should sum up to 1. And we consider a random walk where we put a particle or the walker in the origin here, and we let him evolve. He jumps to right with probability P and to the left with probability Q. So what kind of questions can we ask? Is it true that this random walk is, when it's true that this random walk is recurrent? So what's the, is it true that almost surely the walker returns to 0? And that's true only in the symmetric case, so when P equals Q, it equals 1/2. Then we know that almost surely it returns to 0, so it's recurrent. Otherwise, it's transient. Using some generating functions, one can actually calculate the probability that this random walk, the walker never returns to 0. So if P is greater than Q, then it jumps to the right, and with some positive probability, never come back, but escapes to infinity instead. So then, if psi n represents the position of the particle or the walker after at step n, we can ask what's the expected value. Where do we expect? And this is equal to this quantity, so n times p minus q. So in the symmetric case, it's actually 0. So it should be concentrated close to 0. And we have the law of large numbers, so it gives us velocity, right? So the position divided by time, it converges almost surely to p minus q and goes to p. And again, in the symmetric case, it goes to 0. A little bit sophisticated thing is locally theorems, more sophisticated. So it gives us information. If you pick some integer, k, local theorem says what's the probability. That's asymptotic from what's the probability, more or less, that the walker is at this integer after n steps. So if we take k that is close to expected value, and close I mean like of order of standard deviation, what's further is not important. It has very little probability, so we take care on these integers that are close to drift to the expected value with this amount. So if k is like this, then this probability that the walker, so observe that that's a periodic Markov chain. So at even steps we can be only on even integers. So that's why I put here 2n of a. So this probability decay is more or less like 1 over square root of n times some constant here, and here is also a factor that is, say, it's large when k is close to the drift and is smaller when it's farther. And we have other laws like the law of weighted logarithm, large deviations, Einstein laws, and this random walk is very well understood. So it's a kind of warm-up, and we will be mostly interested in these three questions here. So recurrence transients, the law of large numbers, and local limit theorem, or central limit theorem. Local limit theorem is not. Okay, no questions. We can go further. So let's somehow make our life more colorful, and let's generalize this definition. Any sequence, right, Pj, Qj with these properties here, is called environment, and it gives rise to some random local integers. But this time, the probability distribution, which says where the walker should jump, depends on the position of the walker. So in 0, it chooses with respect to P0, Q0, at 10, it chooses with respect to Q10, P10, and so on. Right? It's clear. Okay, and now proving some theorems in such generality is rather difficult. We can, of course, restrict ourselves to like periodic sequences, asymptotically constant, and so on. We can play a game, right? And then, but there is important branch of probability theory that is called random walks in a random environment. So, what is that? So, I'm going to define certain specific example, right, of environment. So, we fix your favorite measure-preserving invertible dynamical system and some measurable function. Actually, we can have some topology, so it should be continuous. We can have this kind of examples in our minds. This is important that this function here should take values between 0 and 1, right? And invertibility. Okay. So then every point omega in our space dynamical system gives rise to some environment, right? So these sequences, so we take a look on trajectory of omega, forward in time, backward in time. It's indexed by integers, so and we take values of the function p on this trajectory. And that's the sequence indexed by integers. And we interpret this as the sequence of jumping to the right. And of course, this relation here uniquely determines the probability of jumping to the right. Yeah, so, and one approach is like to fix a point, right? You can try to fix some arbitrary point, take a look on the sequence, how does it look like, and then try to prove something, but there is approach that is more fruitful to exploit ergodic theory to prove something for almost every environment. So we can use ergodic theory, we have some dynamical system, right? And we can use ergodic theory to prove like recurrence for almost every omega, or the law of large number for almost every omega, right? So now, for example, this recurrence and transients. Let us assume this dynamical system to be ergodic, and let us assume that this function, this integral exists, where here is the definition of Q, so it is just minus P. And now, if this integral is 0, so we call this symmetric case, then the random walk is recurrent for almost every omega. That's a general fact, and you can find some lecture notes where this theorem is proven. And then if this integral is positive, then we can drift to the right. So actually no, it escapes to plus infinity for almost sure. About drifting means anything. If it's negative, then the walker escapes to minus infinity for almost every omega. So using quadratic theory, you can show this kind of stuff, this kind of statements. Right? Now, and I would like to put emphasis on this word symmetric. So in the sequel, I'm going to use this symmetric word very often. So it means that this integral is zero, and asymmetric means it's not zero.
Can you give a heuristic? Why is it log? Why log?
So, okay, maybe that would be on the next slide. Maybe heuristically. So, in two slides. So, the point is that.
Wait, I have one more question. It might be a stupid question, but okay, it's surely a question. It's stupid. So, can it happen that this integral is not that does not exist? Is there a problem? There might be a problem.
Yes.
If Q is very near zero.
Yeah. So, what happens then?
Or very near one.
Yeah. So that's okay.
What one should be
Below that.
Okay.
yes, so positive part and negative part should be finite. Or at least one should be finite, right?
Yeah.
For the existence.
Yeah.
So if both are
Yeah.
infinite,
Yeah.
then
Okay. So if it doesn't exist, we don't care.
yes.
Okay. So that was my question.
Yeah.
So is there a fourth bullet when it doesn't exist? Something? Okay. It doesn't. Okay. We don't care. Okay. Thank you.
No, but wait, you're right. If it doesn't exist, we actually don't know.
Yes. So
Okay. So if we then we don't know. Yes.
And then I guess then the question is, why did you choose log? Because maybe if you were to choose another function, you could give a wider characterization.
I don't understand that story. If it is plus infinity, then it escapes to plus infinity even faster. If it is minus infinity, if it is minus infinity, then the walker escapes to minus infinity
Yeah, but,
even faster.
can't you
What's
have
the problem with finite?
Can't you have both part going to infinity with positive measure, part going to minus infinity with positive measure?
Is somewhere 0 and
Yeah, so
somewhere
like this.
1. Okay, yes. Then basically then it is not random.
Yeah, that's
You can have some trajectories which go this, some trajectories which go this. And
Yeah, I
so
assume there's no like standard behavior now.
Okay. I hope you clarified situations. So answering to your question, when you so in the proof for probabilistic reasons appear say something like this. So it's say and here is ix qx x plus j alpha or minus j alpha q of x plus j alpha. So this
J or N?
yeah, N, sorry. So for some reasons from probability theory, convergence, for example, of this kind of function is important. So when I know that the logarithm is negative, then it should converge for almost every point, right? And it gives us some other, so that's heuristic, right? Because this kind of quantities appear, and when we apply logarithm to that, that's Birkhoff sum, and then we can use quadratic theory. But in the next slide, I think there will be something else that's helpful to understand. Okay. So more questions? Oh, okay. Now we have measure invertible measure present dimension. Okay. And So the recurrence and transients is clear. Okay, that was on the previous slide. But now the law of Dutch numbers. And now it's there's very important tool that is called the environment view by the particle process. And this tool is certain auxiliary Markov chain on omega, so on the same space where our dynamical system lives. And studying this auxiliary Markov chain may be useful to prove something the original random walk. And now transition probabilities. Okay, so you see we have just some dynamical system. Here is point omega, and from this omega we can move to the point t omega or to the point t inverse omega. And this happens with probability p of omega, and this happens with probability q of omega. That is defined by 1 minus q. So we have just trajectory on our random walk, and we move on this trajectory in a random way. And this process is called the environment viewed by the particle process, EVP for short. Okay. Let me mention also that it's not that, for example, we can ask what's the stationary measure. If P is the stationary measure for this auxiliary Markov chain, but unless the situation is trivial, like P is constant or something, then it's not the case. It's really, this measure changes. So it's not, investigating stationary measure is not so easy to do. And now,
does this just correspond to fixing omega and then saying what's going on? I didn't really understand the point.
No, so the point is that we have a space omega, and on the space omega you have some function, transition probabilities, right? And you can consider Markov chain starting from some fixed point, from some stationary distribution, right? So
the family of dynamical systems parameterized by the structure.
Yes. So that's a transition rule, but of course I didn't specify what's the initial condition. So but do you understand this definition of Markov chain? We have just transition probabilities, right? Okay. Yeah. So maybe now. So we dealt with recurrence and transients, now the law of large numbers. That's the application of this AVP process, how we can use this. That will be sketchy. So let's assume that this expected value is positive, right? So we have the case where the walker tends almost surely to plus infinity. We define this kind of function. And as I said here, the existence of this function, that the convergence, right, follows from the Dolgopyat theorem. And so that's some function, and let's assume that it additionally has finite expectation. Then this drift is equal to this. Right? So the law of large numbers says that psi n over n is the inverse of this expected value on this drift. And why? How to prove this? And again, that will be some sketchy argument which explains what kind of which motivates the sequel. What happens to the sequel? So the proof. We have this Markov chain here, AVP process for this random walk. Under these assumptions, one can find absolutely continuous stationary ergodic measure with density lambda. So actually you can write down density explicitly, and it's more or less similar series. It's not the same, but it's quite similar. And that's a stationary measure with density for this AVP process, right? Then we can decompose our random walk, so psi n can be decomposed as a sum of martingale that is going to be negligible. So this mn is something not important, and then d, that's some function on omega, but what appears here, that's a Birkhoff sum, but not of psi n, but of this AVP process, right? So the behavior of this will be governed by the integral of d. Right? if we know the integral of D, then we know how this behaves, and because Mn is negligible, then we know we can know the assertion for psi n. And so in the third step, we can calculate just that this integral of this function D that appears here with respect to this invariant density is this. And that's the end of the proof. As I said, I don't want to be precise, I really explained it in the text, but that's more or less flavor. So it's important, for example, for the sequel, that it's nice when you have absolutely continuous stationary measure, right? It's useful to have this. Okay. What's next? Okay. That's actually kind of regression. So central limit theorem. So we can prove in the asymmetric case we can prove central limit theorem under stronger assumptions. And I'm here a bit sloppy actually because there is probably the vast literature devoted to this, and the statements are not really as precise as I said before, precisely as I said before. So I'm cheating here a bit, but more or less to remember that in asymmetric case we can prove central limit theorem. That looks a bit maybe different than presented. In symmetric case there is no central limit theorem in general. Instead there is something that is called Sinai localization. So it's not important, you don't have to remember this, it will be not important, but it's quite fascinating that in symmetric case, Sinai proved that under some additional assumptions, so this dynamical system actually should be, this PI should be IID sequence, and ellipticity, under some ellipticity conditions, so it's not important, but it's important that this random walk is concentrated roughly on the interval of it's concentrated. After dividing by the square of logarithm, it becomes close to some point. So this random depends on the environment. So you see, in standard CLT, you have like normalization by the square root, but here the square of logarithm, natural logarithm, is sufficient, and then it like collapses to a point. So it slows down. The random walk slows down in symmetric case. So that's a kind of regression. As I said, it's not really important for the sequel. And now, quasiperiodic environment. So we take my favorite dynamical system, invertible rotation, circular rotation, and so we have X, our reference measure is the Lebesgue measure, circular rotation, and as I said before, we can either, like, for every point, take for example, I don't know, 1/2 plus epsilon cosine 2 by alpha, this kind of sequence, and alpha, and consider this as an environment, right? And try to prove something directly, but also that would be a problem maybe for Hardy. But we can also use ergodic theory to prove something for almost every starting point. Once P and alpha are fixed, we can try to prove something for almost every point. Lebesgue almost every point, because every point is the invariant measure. And now the AVP process is this. So this random walk that I described in the very beginning, roughly announced. So we have this function P on the circle, taking values between 0 and 1. Q is just 1 minus P. And now we have transition rule that if the walker is at the point X, then we can jump either to X plus alpha or X minus alpha, so it means rotation, right? Rotation of angle alpha. And the first happens, this happens with probability P of X, and this with probability Q of X. And now we can actually ask the standard questions like, is the system ergodic? Is it stable? The rate of mixing, and so on. So it's interesting by itself, right? But what I presented before, like, it gives certain context for that, quite important motivation. Okay, now formally the transition probabilities. in the sequel I will use this notation, so it will be the capital T represents this Markov operator here. If I will recall it if necessary, so it is operator on the space of, say, continuous functions, right? Which gives the expected value of phi in the next step. Okay. Next, what do we know? So there is some general theory that you can apply and deduce something, but maybe that's very nice dynamical system. You can measure a Boxman inequality. You can solve the Diophantine equation, homological equations. So maybe you can prove something directly for this dynamical system. And now let's assume that alpha is Diophantine. I need to recall the definition. If P is smooth, actually sufficiently smooth is sufficient, but let me keep it simple, then the local limit theorem holds for every point x. So we started from the random walks in random environment, and then this first part of this theorem is about this random walks. So for every actually, as I said, this general theory provides usually something for almost every point x, but here we can prove for every point x, not for almost every point, but for every point x.
But this relativity you define on the line, not on the circle.
Yes, that's on the line. Yeah, that's on the integers. So this first part is. And now for this AVP process, the second part is for the AVP process. So there exists a stationary measure for AVP process that is absolutely continuous, which is the measure. Right, so it's very nice, so it should be. It's uniquely ergodic, so this absolutely continuous measure is actually unique among all stationary measures, and the system is stable. And what I do mean by stable, so for every starting point, this integral converges here. So we can do this integral. So it says that no matter where you launch your process on the circle, the position after n steps, that's a random variable, right? And this random variable has distribution close to the stationary measure. That is what this stability means. And you can call it also mixing. So that's it. Sina results, that's first. Okay. Now, Sina Kaloshi, if P is asymmetric, continuous, then the same assertion holds without the assumption that alpha is Diophantine.
So for any alpha?
Yes, irrational.
Okay.
Yeah. So the previous theorem of Sina, you see, it doesn't matter if P is symmetric or not. So it doesn't matter if it's recurrent or if it is scaled to infinity. But here they prove if P is asymmetric, then actually the same holds. Actually, to be honest, the local limit theorem, so this theorem for the line, is a bit different because you lose something actually, but maybe let me not focus on that. Now, Bremont. Okay. Let me go back to the later. And now, what we don't know here, so I will go back to that later. And for this, so Sina and Kaloshi proved that if alpha is if P is asymmetric, then the situation is nice under control. So and when alpha is Diophantine and P is symmetric, then it's nice. But what happens when alpha is Liouville, so not Diophantine, and P is symmetric. And they proved a bunch of theorems, like 6 or 7 theorems, which says that actually so that was, you can see here is a meta theorem or some heuristics. If alpha is Liouville, then this behavior is erratic. So it's erratic both for this random of integers on the line, and on the circle.
What do you mean by erratic?
Yeah, so for example, they proved that if fixed alpha uv, then for generic p, there is no limit theorem for this process on the line. So no matter how you rescale your process, there will be nothing in the limit.
Generic P is in which class?
C infinity. And it's the AVP process also is erratic. So they proved, and that's precise statement, if alpha is really then for generic P, there is no absolutely continuous stationary measure for this AVP process here. Okay. And so after this paper, there is still something unknown. So they didn't deal with the question of unique ergodicity of this AVP process and mixing of the AVP process. So you see that Sinai here, he proved mixing and unique ergodicity, but it's, so let's say that they didn't know, the authors didn't know that when alpha is linear and P is symmetric, is this AVP process uniquely ergodic? Is it mixing? They don't know, and they posed it as a question. So I managed to solve this. So if alpha is irrational and P is C1, then AVP is uniquely ergodic. So this part of the question is solved. And now, unfortunately, then, so that was my previous talk here. I was describing these results. And after that, so after the talk, I realized that it was proven by constant diverge. And actually, the statement is more general. So if P is symmetric and log P of Q is continuous or bounded variation, then the AVP is uniquely ergodic. And why this assumption is important? Because we can use the Rao-Cox inequality. So, you know, there's this result of proving that circle default is ergodic with respect to the back measure. And that's more or less the same idea. And now, okay, so here, yeah, going back, so the order was wrong, confused the order here. So Bremont proved that there exists continuous P symmetry with infinitely many atomic stationary measures. So he proven that it is the proof is sharp here. And Chevalier, for higher dimensional torus, he because you can of course formulate the same, you can have torus rotation and consider the same questions, and Sinai result is the same. Sinai evaluation result is the same. This result for the Dolgopyat is original also the same. But this result by constant diverge is not the same. And my result also doesn't cover higher dimensional torus. So the situation for higher dimensional torus, I mean unique ergodicity, is a bit different. And Chevalier proves something, and it's a bit strange result because he constructs, so he fixes some, he says that for take an angle alpha, irrational, then I can construct a counterexample. And there is a second part of this theorem. If alpha is additionally Diophantine, then the counterexample can be Lipschitz. So that's strange order. You see this usually when you prove counterexamples, when you assume alpha is Liouville, so when alpha is not Diophantine, you can prove better regularity of the counterexample. Here is the other way around. That's strange. So that's why I wanted to tell about this. And actually, I can tell you that constructing these atomic measures can be, it's about just construction of a function phi, f, from the D1 to R, with the property that sum over all integers x, Birkhoff sum, say 0x, okay, x is finite. So if I construct this kind of function such that for some point x, this sum converges, then I can construct probability function phi using this function, for which there is atomic measure. And this atomic measure is concentrated on the orbit of this point. So you see, the Joule-Coxman inequality contradicts. Like if you assume F to be continuous of bounded variation, then the Joule-Coxman inequality contradicts this kind of construction because it is infinitely it is bounded, like closer than some number n variation of F, right? Infinitely many times. So this is bounded from 0 by some number for infinite amount of n's. Right? So it will surely converge. This diverges. Okay? But in higher dimensional version, you don't have the Joule-Coxman inequality, so maybe you can hope to prove something better. Like maybe I would be interested to see if it's possible to construct a function, like an analytic function for some angle that satisfies this.
The integral of 0.
Yeah, of course, yes. Thank you. Yeah, so it would be nice to have this kind of function. Okay, so that was the Morales regression also. And now, okay, so somehow you see this result here, like the quality of this result dropped significantly. So I tried to rescue it somehow. So I proved mixing, but for generic symmetric P in C1. So it's not so nice result already, and it's and now main results. The first result says more or less that if X is compact and you have any iterated function system with probabilities, if you know that the system is uniquely ergodic, then it must be mixing automatically. So let us fix some general space X and some functions. So that's our transformations rules of moving, and we need to assume that J1 should be identity. So one of these transformations should be identity, must be identity, that's necessary. X is compact, that's also necessary. Okay. Then we have continuous functions, so it actually depends on the point. These are functions, they depend on the point on X. And it gives us the probability distribution for every point, right? And now we have clearly some random walk. Here, Markov process on X. Yeah, iterated function system of probabilities. If this random walk is uniquely ergodic, if we can prove something based on somehow this, and this condition means that you see G1 is identity, so P1 is the probability that we stay in where we are, and this probability should be uniformly bounded by some eta from 0 and 1. So this says that our random walk is in some sense lazy, like we don't want to move with some positive probability. Then the random walk is also stable, in the sense that I described in the sense, so mixing, right? Stable mixing is interchangeable. Okay, and now, so it applies to our result, to our system, when log P over Q is continuous with bounded variation.
So I don't understand, where are you walking? You have now other choices. Yes?
Yes?
So are we on the R-dimensional lattice?
No, sorry, so that's confusing. Now, from now on, I think I'm only going to discuss this process on the circle. So we should have this dynamical on the circle, forget about the line. So here you have like finite, so that's our circle, and it would be like rotation one direction and the second direction.
can be, I don't know, 10.
Yes, yes, so we can have arbitrary number. If you can prove unique periodicity somehow for this system of rotations, yes, then you can prove.
So it's the same transformation, just
So this is an abstract result which you then applies to the circle.
where you only need one.
Yes, on the circle there will be one forward, one backward.
Yeah. Actually, three, because
Three.
you need to
One.
consider
And
the
then-
second iteration. You need to consider, right? And then this assumptions are satisfied. Yes. So R is not the dimension of the lattice; it's just the number of transformations.
So, sorry, can you hear me? A question. So here in this theorem, you have a condition that you have one trivial action, right? With positive probabilities. So with positive probability, you stay at the same point. Is this correct?
Yes.
At each step. I see.
You mean, sorry, sorry, can you repeat the question?
So in this theorem above, you have G1 equal to identity. P1 of X is separated from 0. So with positive probability at each point,
Yes.
in one step, you stay at the same point, right?
Yes.
So this is different from what you have with these two, P and Q. So how do you apply this?
Okay, you need to consider second iteration. After two steps, you can jump either to X plus 2 alpha or X minus 2 alpha or stay where you are, right?
Oh, I see. Okay, I see. Thanks.
Okay. Thanks. Okay.
So without this assumption on P1, we look at counterexample, this theorem is false then?
We tried to prove this, but I didn't find any contrast. Yes. Initially, we had intuition that it should be true, but I don't have comparison. Okay, now, very. Don't read this. It's important. We have here some equations. So let me recall that P phi of x equals P of x phi x plus alpha plus Q of x. So now the previous theorem was general for general dynamical system, but here we have just a circle and this process here that I defined. So x, we have some fixed function P from the circle 0, 1. That's fixed. Okay? And we deal only with this random walk here. T is here. Okay. And now we have this kind of equation that is called a Poisson equation. So here, psi is given, and you need to find psi is given, and we need to find phi that satisfies this relation. We assume psi to be sufficiently smooth and the integral should be 0. Why should we care about this? Because when we can solve this equation, then we can prove actually central limit theorem in this case. So I take psi, if I can solve for psi this equation, then I can show also the central limit theorem for this process. So this divided by the square root of n converges to central to the normal distribution. And that's in stationary case. So xn should be here the stationary measure for this Markov chain. So that's why it's important, right? First of all. And we can solve this if alpha is Diophantine. And we should assume that P is sufficiently smooth, psi is sufficiently smooth, and so on. So, and here is the precise statement, but it's not, I think it's not very important to remember this result. It's important that we can, if P is sufficiently smooth and psi is sufficiently smooth, then I can find a solution phi that is also smooth, but some smoothness is lost. And I have also estimate on the norm So this norm cannot decrease. I mean by this one, this statement. And what's here also interesting is that in symmetric case you lose more smoothness. So asymmetric seems to be easier to deal. Again. Okay. So one consequence is, of this previous result is the central limit theorem. Immediately, that's easy consequence of this theorem. And then actually you can also estimate the rate of mixing. So again, you need to assume that alpha is Diophantine. Yeah. And P, it doesn't matter if it's symmetric or not, really. But we know that this thing converges to integral with this rate. So, if you want, the point is that if you want, k here can be arbitrary, but then, so you can give me k, and then I say how large R should be for this result to hold. Okay?
Solution of the equation.
No, here no. Now there is no equation.
Homology equation.
So no, so psi is our. We wanted to solve the equation for psi. And actually, to prove this result, it's important to have this solution.
And phi.
Yeah. Yes. So yes. Okay.
So if we want better speed, we need some more smoothness.
Right. But it's like generally it's kind of polynomial. Okay. Now, did we prove anything more? Yes. Here everything is clear. I mean, roughly. Okay. So counterexample. So if alpha is trivial, can we prove something? Some rate of convergence.
If you look at like linearization theorem.
Yes, that's right. So if alpha is trivial, then we can, and p is actually an arbitrary function, satisfying this condition. Then there exists psi and set of positive Lebesgue measure on the circle, such that for every point, if I launch my process from in this set, right? Then it will be not polynomially mixing in this sense. So there will be infinitely many ends for which this is violated, no matter how beta is small. So, fine. Something about the proof. So this proof of the first theorem is quite nice. That's quite a nice idea.
Which was the first one?
Yeah. So it was this general result about mixing.
With the homology.
No, before, it was before, so maybe let me recall it. Okay, that's this result.
Okay, that's the first.
So you have some arbitrary iterated function system of probabilities, compact space. If you know it's uniquely ergodic and lazy in this sense, then it is also stable. That's what we are going to prove.
Well, it's not very lazy.
It's not very lazy.
If p1 could be equal to 1, that would be very lazy.
Yeah, definitely.
What you understood by stable?
So stable. Yeah, so it was this convergence for every starting point and for every continuous function. Ex phi, so it denotes the expected value provided that we started the process of x, but it converges to the integral with respect to the unique stationary measure. So we have this general dynamical system, random dynamical system with this transition probabilities here. And now, accelerated walk. that will represent our space, and that represents time. So we can start here. We have some point in our space, time 0. We can start here, and then we jump, say, to some point, right? And then it's important that we have identity among our transformations. So with some positive probability, we can stay where we are, right? So in this state, it may happen twice or something, but then we move again, and then we can stay or not. Yeah. And if I want to have accelerated random walk, then I just remove these repetitions here. This, right? Because I'm here, so I remove this part until I finally change the state. So I remove also this because I was here. So I leave it normally, and here I stay, so I remove this, and so on. So the accelerated path should be something like I move up, I forget about this, I move up again, I forget about this, so I move down, down, and then I forget about this. So it will be like this accelerated. So that's the construction. And now, if I give you a trajectory, right, then I can produce this accelerated path. But given accelerated path, I can have many trajectories that pass through it. And the length of this, so how much time it takes to traverse this path, is a random variable that I denote here by the W. Okay.
So by segment you mean this segment of time on this left the graph.
By segment W, I mean like this sequence of positions.
Okay, so you don't mean like a segment on the circle or something. No, that's not.
It's the
That's not true.
it's the finite east of the original trajectory of the random walk.
Yeah, which behaves with the set monotone conditions on the monotonicity. Okay.
Yeah, I would say that this is the sequence of points in our space, right? Sequence that represents the order when we pass, but not how much time do we spend on each.
Being lazy.
Yeah, being lazy. So TW is this random time that it takes given segment. We have this finite time, random time, and this is actually a very nice random variable because it does a sum of geometry of random variables with geometric distribution. Why? Because when we are at some point here, then we leaving this state is like the success. Yeah, so this process is just the waiting time for the first success in Bernoulli trials, and that's a geometric distribution. So the point is that it has very nice descriptions. It's a very nice random variable. And now capital T W is just the expected value of TW. So now let's fix n large. Right, so we have a bunch of trajectories, and for each of these trajectory, I can define tau to be the first time when this accelerated walk has expected value greater than this. Okay.
Was eta given before, or is it just
Eta was in the statement, so that's this coefficient that describes how lazy it is.
okay.
Right?
Okay.
And I need to take some eta by 2 because it's not the case that for every trajectory of length n I can define tau, right? Because I can have just one trajectory is so all the time I stay in the same point. And then the expected value never increases actually. So I need to, so this eta is to ensure that with large probability I can find tau before n. So let us try to estimate this expected value of psi. Okay. So this here represents all possible accelerated walk segments. All possibilities are denoted here. And we sum over all these possibilities, right? And here is the probability that our trajectory takes this accelerated walk segment, right? When we know this accelerated walk, then we don't know the time, how much it takes this trajectory to pass. But this is described by our, by this factor. So it's k probability that t w equals k. And what is nice, that if I know this accelerated walk segment, then I know also the endpoint, right? So this endpoint doesn't depend on this time. It depends only on the choice of, on this w, capital W. Okay? So here, n minus k, that's because tw equals k, right? So I still have n minus k steps to do. And it's something not important here. EW represents the end. So that's, yeah. Can I explain you something more here?
Reminder are those trajectories for which this time was larger than n.
Yes. Okay. So now we divide integers into small intervals of length delta square root of n. And okay, so I don't care about this part. And now I'm going to estimate that this part is actually, so for every this segment w, this part will be close to the Birkhoff sum, or Birkhoff average. Birkhoff average. If it's going to be close to Birkhoff average, then it will be also close to the integral. So the expected value. So I take this on only this part that is interesting to me, and that's only changing of notation. So there's this operator t, and I can iterate this operator, and that's just a changing of notation. Actually, t can be defined in this way, right? So nothing happens. And now, here also nothing happens because I only rewrite this summation in some more fancy way, first over intervals and then over k in each interval separately. And now what is nice? What is nice? Because as I said, TW is a very nice random variable, that's a sum of geometric distributions. Local limit theorem holds for this sequence, for TW. And if a consequence, I don't need really delta limit theorem. What I need really is that on this interval of size delta square root of n, because delta is very small, so it's a very small interval, TW is more or less equally distributed. Right? So if I want to know if I have some k in IS, then this probability equals more or less probability that TW belongs to IS divided by the number of elements in IS. But there is a nice consequence because it looks like Birkhoff sum, Birkhoff average. And that's actually the consequence. Now we use compactness, unique ergodicity, and we know that for every starting point, this convergence is uniform, right? If the system is uniquely ergodic, space is compact, everything is compact, then the convergence in Birkhoff ergodic theorem is uniform. So that's, here we use this fact. It is close to the integral uniformly, no matter where the endpoint is. So this probability here doesn't matter here, and yeah. And that's the end of the proof actually. Okay. No questions?
Not getting somehow on the heuristic level why stopping at some times improves the convergence. Somehow intuition would be that if you don't stop, then you should converge to the same frame but faster. I understand that the proof very strongly uses the fact that this stopping somehow distributes the frames in time. You can be here this time, but you can be here sometime later, sometime. And so on.
So it's I'm a bit confused because I'm not saying anything so far about the rate of convergence. You're saying faster.
I'm saying about rate.
Okay.
Stable, that is, it converges. Yes, but you would think that if you don't stop, then you should converge to the same place, but faster. I do not say much faster, but it should not stop you from converging.
Okay, so
Somehow, I don't see.
I see. Well, maybe later I will be able to explain that more carefully, better.
It prevents the quick jumps.
Yes, it's something. This is smoothing things
The
out in
distribution
time.
in values is the same, but the speed of jumps is smaller.
Concentrated at some strong positions. Every trajectory suddenly goes there, or every trajectory goes there, and when you add those stopping, then you distribute, you somehow shearing your distribution along the path.
Yes, probably. Yeah.
It's probabilities of being at every point more uniform.
Yes. Smoothing things out on each particular trajectory.
Like
If you not one trajectory, but a bunch of trajectories,
And you
because of those stopping times, they are somehow time
On average.
translated with respect to each other.
So
but it does look strange. Forcing to get some statistics here.
okay. So everybody's happy now?
Yeah, sure.
More or less, okay.
Sun is shining, everyone.
Okay. Now, so I treat this theorem, it was sketchy of course, but it's more or less proven. So that was this first theorem about the rate of convergence. So, okay, so it was this theorem. Now there's a second theorem, this Poisson equation. It's, I'm going to present you the solution. It's, well, you just need to understand more this left-hand side, do some trick, decomposition, then solve cohomological equation, then again solve cohomological equation, something like this. Nice, but maybe I can show you it on some other occasion. This theorem, okay, now this counterexample also is like, I'm not going to present this, but let me just show how to prove this and then leave you. Okay, so proof of the fifth theorem. First, we define, so we keep our notation, we have this TW, and we define inductively, well, there is no induction here so far, but here is important. So delta 1j, it will be the difference of these probabilities, right? For neighboring j's. And so on, and for higher order, that's clear definition. Okay, it's important, so.
I'm not saying anything.
But you're confused, so is
Yeah,
it
I'm
clear?
trying to understand it.
Yeah, it's important, so. So delta 0 is just the sequence of probabilities here. And then we define the sequence of differences of neighboring. Then we obtain another sequence, and then again differences, and so on. Now we had our psi, so we use theorem with the proof that I didn't explain to find this phi. And I have control of smoothness of phi and null of phi, right? Then I start again. I need to estimate the rate of convergence of this to the integral, right? So I use my cohomological equation and I put that here instead of this. Right? this appears is kind of this. So here is here's phi, right? And that's the consequence of this Poisson equation. Now I do a Abel summation trick. So these are these border values, and here is the sum that remains. And that's why I define this sequence delta j, because what is here are these differences of probabilities, right? Okay, so this is not important. I have this to deal with. Okay, and now I focus only on stuff that is close to, it should be eta actually here, I believe. So that is close to the drift, to the drift of this value. So everything that is beyond has very low probability. This kind of, we have this kind of moderate deviations. That has not very, we can focus only on this. Okay, and that remains. That remains. Okay, and this is why this is nice, because this is bounded by the norm of psi, by the norm of phi, but also by the norm of psi. So because we have this theorem, number of elements, right? And then there's this maximum value of the delta j's. And the key point is that we can prove that this sequence decays like 1 over n. So if I started from the locality theorem, and then this probability of being at each integer is decayed like 1 over square root of n. But if I take the difference of probabilities, then it decays like 1 over n. And this gives us this right here. So that was like for k equal 1. If I want to have higher k, then I need to take a look on this sequence and solve Poisson equation for phi, get another phi 2 or something, define inductively here delta 2j, right? I did this, and apply the same trick. And that's how I improve the rate of convergence. Then I need more smoothness, of course, but it's less. So yeah, so that will be the end. And now some questions for the end. So Bernoulli property, if this AVP process satisfies the Bernoulli property, and that may be good for you for discussion, because it would be nice to have some estimate for Hausdorff dimension for stationary. So, for example, is it true? I know that it's like absolutely continuous in most of cases, so asymmetric case or symmetric Diophantine cases. But maybe if I fix some Liouville alpha, then for generic P, the stationary measure has Hausdorff dimension less than 1. This kind of, I would like to know if this kind of theorem is possible to prove. And the only hope is like use of Boschert-Nician theorem of this. I don't see other strategy. So that's why I mentioned. Okay, so thank you for your attention.
Are there any questions?
There's a small remark. So I understand in this first theorem, if this G are, for instance, homomorphic, and you assume that there is G, some G, and the inverse of G, then you have your assumption, yes?
Yes.
Because
Yes.
you stay with positive probability.
Yes.
You don't know.
Yes, that's right. There were some questions during the talk, so.
No questions online?
No one speaks anything, so.
Yes.
Maybe I'll return to this point that confused me. okay?
Uh-huh.
So in this theorem, you are walking on the circle, and these functions are defined on the circle. But in the original setting, it's like two different spaces. There is the space where you are doing the walking, and there is the space where you have these functions coming from, right? Did I get that correctly?
In my original setting, I have just two functions. It was t and t inverse. So my
Yes, but you had another, you had a probability space omega.
yes,
Which is not the space where the walking is happening. The walking is happening on the line.
yeah. So I had like two random moves. The first, this initial was on the line, and then there was auxiliary tool, and it was this random walk on omega.
Right.
And so the point of this first part was to prove that investigating random walks on omega can help with investigating random walks on integers on the line. And then whatever I thought later, it was about, I think, this random walk on omega. So we could forget about line, just omega.
Okay, are there any other questions? So if not, let's thank Klaudiusz again.
Still in Austria?
Still? Yes.